Welcome, everyone. Good morning, good evening, depending on where you're connecting from. My name is Sebastian Rivera, and I am part of the author team of this uh, selected paper. And as you can see, it's composed by me, which I am currently at the Delft University of Technology as an assistant professor. Uh, I'm Today I'm joined by Stefan Gutz from Cambridge University and Samir Kouro from Luxembourg Institute of Science and Technology. Unfortunately, Peter Len from the University of Toronto is not able to join today, and the same goes to Mehanathan Padmanathan. And in shortly, we should have the company of Professor Pavel Bauer, also from Delft, and Rosa Anna Mastromauro from Università di Firenze, Italy. So just to get you acquaintance with the faces that participated in this uh, paper. So we have a sort of a four-section webinar today. I will start with a little mild introduction on how electric vehicles are charged, and then how the charging infrastructure it has been accommodating to these particularities. Then the second part will be taken by Dr. Kouro, and he will focus on a much more topological aspects of EV charging. Then Stefan will take over and discuss some interesting aspects regarding the grid integration and how we can make the most out of this permanent electrical equipment connected to the grid. And finally, I will wrap up the session and give you a bit of a what is our outlook in terms of technology for the future years to come and the current challenges, and more important. So having that said, I'm pretty sure that everyone has here that there are many types of chargers, different classifications, different power levels, and so on. But from a fundamental perspective, the task is relatively the same, regardless we are dealing with a high power fast charger located in the highway, or if we're just charging it from the home outlet in our houses. And this fundamental principle is that the battery inside the vehicle is storing energy at DC, and most of the time we need to charge it from an AC grid. So inherently, there's the requirement for having some form of power conditioning that will turn this alternating voltage into a DC voltage that will satisfy the requirements imposed by the battery management system to safely and successfully recharge the battery. Of course, the fact that we use our vehicles differently in different countries, and also it depends from person to person. Uh, of course, the context of the possibility of recharging the vehicle will impact the way the power conversion happens. So for EV users, most of the time they will use their EV normally during the day, and then when they get home, they will recharge it through a possible limited power connection in their houses. So this will give rise to the so-called slow charging, because you don't have that much power installed in your house. And also the onboard charger will also have a limitation in terms of how much power you can actually inject to the battery. If you are also able to, let's say, find a three-phase outlet in the neighborhood or surrounding areas of your house, you could recharge slightly faster from a three-phase AC supply available throughout the cities. Naturally, the access for a three-phase supply also allows you to maybe charge a bit more fast, because you have more power available in that installation. And if you're running out of time, or if you are in the middle of the highway and you need to make a quick stop to recharge it, you are able to inject power into your vehicle already conditioned at DC by a specialized unit installed outside the car, which is an off-board charger. The difference on how the energy is introduced into the car also leads to labeling AC charging because the power enters into the vehicle in the form of AC signals, or DC charging. But we don't have to forget that the batteries are always DC and there's some conversion hidden along the way. Okay? So yeah, we have different types of charging and also different rates of we can charge. And this has been listed in many standard and standardizations. Organizations have made efforts to classify the different levels, which kind of gives you a hint on how much power we can actually inject into our vehicles depending on the type of supply. And it's always easy, or it's always nice to, when you're starting a new topic, to have a broad classification to understand what is the context for each charging method, and also and that context kind of defines the way the technology for supplying such a system it's deployed, right? And despite the many standards shown here, like we have one line, one different standardization or one standard document, we can clearly see that there's a common agreement that for lower power levels, AC charging is the way to go. You will use the equipment already designed for your car and for that particular battery, and you're just connecting to some form of AC supply. And beyond that point, all the DC options, all the charging options that imply that the power conversion takes place outside of the car or off board will allow you to reach higher power. Of course, the development of this standard goes along with the battery technology, because 10 or 15 years ago, batteries were not as capable as the batteries that we can find right now. So if we jump a few years forward, we can see that the power levels or the maximum power ratings where we can actually charge the car are getting higher and higher because batteries are able to withstand such stress. And now it's common to hear that it's expected that heavy duty vehicles such as logistic or freight trucks should be replenished by megawatt chargers. Okay, so we need to keep that in mind, that one thing is the context of how you charge your car, but we also have to have in account that each vehicle has different energy usage and also different types of using it. So of course, each level or if each class of vehicle will aspire or will be charged through different power levels. So you cannot compare the power requirements for a city car, which typically will charge below the 100 kilowatt range, or what you need to quickly recharge a truck in a megawatt rate, or even 5 megawatts range where we are talking about vessels or mining equipment. So yeah, each type of vehicle also leads to different types of charging, and that will imply differences in terms of what kind of circuits are used for that power level and so on. And finally, despite the charger can have certain power rating or certain label that it's capable of this many kilowatts, it is the vehicle that ultimately sets the actual power getting injected into the battery. Because as I said before, there's a specialized equipment inside the battery developed along with that battery and that monitors and makes everything in such a way that its lifespan will be maximized. So it is ultimately the vehicle that decides or that imposes what type of charging rate we will be using. So the paper focus on the role of power electronics in the electrification of vehicles, and then it's inevitable to start looking at the topology or the morphology of each type of charger. Since the car is expected to be manipulated by a person, it is imposed by standards that some form of isolation should be deployed within the power conversion lane. And mostly we have two options that dominate the system. One would be deploying the isolation at low frequency transformer at 50 hertz with a bulk transformer at the beginning of the station, or you could opt for a power electronic transformer or a high frequency or medium frequency transformer that will include that galvanic barrier in the middle of the power conversion. and that could alleviate some footprint problems or some leading to smaller solutions rather than a low frequency one. And finally, this basic function of turning AC into DC suitable for the batteries, it's done in 5 major categories. And we can classify them as where the line of my vehicle ends and what it's outside the vehicle. So as I said before, AC charging methods are just getting AC from outside. So besides some form of switches and relays and protecting devices, the power conversion happens inside the vehicle. And you have some options where there's a specialized dedicated charger that does every possible task to turn AC into DC for the battery. And in some other cases, they use part of the drive that it's idle when the vehicle is stopped and reconfigure it as a charger. Then we have wireless technology that kind of breaks the charger in the middle, and I have a grid connection and the transmitting inverter outside the vehicle, and then the receiving rectifier and the rest of the protection system over the vehicle. And finally, the DC charging solutions, they take all the energy and all the conversion happens outside the vehicle, and the vehicle is just getting the DC quantity that has been precisely set by the BMS. And finally, there's a charging option that takes place completely outside of the car, and it's when you're able to remove the battery and replace it for a charged one, much more convenient. Okay, so the paper is about power electronics. So what we did when we wrote this thing is that try to make a common idea of what charging does and then get into the context of each type of charging. But overall, you can see that how the basic function of turning AC into DC controllable, it's fulfilled in different manifestations. The first look, the detailed look that we gave, it's one of the most common way of charging the vehicle through the onboard charger that is located inside the car. And we can see that despite the requirement is going from AC into DC, this is not done in a single stage. Why? For many aspects. One, the simplest one is that if you do a single stage charging converter, you will have to be able to control energy coming from the grid in the full voltage range of the battery. And that is not always the case because we have vehicles with 800-volt batteries and vehicles with 400-volt batteries. So a pure rectification stage is not always possible. It could be for some cases, but it's not the standard way of doing it. So for deploying this in the vehicle, you need to be compact and small. So mostly you will see onboard chargers with high frequency isolation. Then if we have DC charging technologies, all the power conversion happens outside the car. So you have more freedom in terms of bulkier equipment and larger footprint. But that's just a maybe, because you have to also think that the landmark and the space that your charging station uses, it's also have to be taken into account to actually be profitable. And we highlighted two representative industry cases. One, it's based on low frequency isolation. So we can clearly see that the simplicity was one of the major drivers in developing this charger, because it's basically using really fundamental and simple power converters. And another relevant charger that was for many years like the best-selling charger within the category, chooses to deploy the isolation at medium frequency and also shows this trend of breaking the charger into functional units that can be built up as a Lego. So you can satisfy a broad line of products by using the same fundamental product. In this case, a 30 kilowatt, a 90 kilowatt charger or 180 kilowatt charger, it's done by blocks of 90 kilowatts each, of 30 kilowatts each. Okay, so depending on the way you want to deploy these chargers, the most relevant one was to study DC fast charging stations, right? And regardless, they use low frequency isolated solutions or medium frequency isolated solutions, they fall within the same type of layout. And it's through a medium voltage substation, you enable a local 400 volts AC grid, and then you connect each of the charging stalls to feed as many vehicles as you would like to. Alternatively, some vendors have decided to go for a larger common rectifier unit and deploy the charging stalls through local DC buses. That kind of makes the case when you want to gain in terms of footprint or efficiency. However, the rise of higher power levels that were unthinked at the very beginning or at the very first years of this third EV era, it's posing the question like, it's this way of just putting more chargers in parallel to reach higher power the way for the future? So that's one of the questions we posed in the paper, and also highlighted how some efforts of making a reality the megawatt charging capability actually went for much more sophisticated converters. And the sophistication of the power conversion stage, it will make more sense as we get into more and more grid service requirements that it will be covered in the following section. Okay, that's my section, and I give the turn now to Samir.